Assalamualaikum and hello. Welcome to our video presentation. We are Group A. We'll analyze a critical but often overlooked safety issue in modern vehicle production, fire hazard caused by structural adhesive failure, based on real-world record from major OEMs such as Ferrari, GM, Honda, and Ford. Our group consists of 5 members. First, me, Hakim, Zafri, Amiza, Aiman, and last one, Imran. Together, we prepare this project on automotive fire hazard caused by adhesive failure.
Hi, my name is Muhammad Imran bin Abdul Rahim. My matrix number is CN230069. I will begin with introduction for this presentation. The modern automotive industry is shifting from traditional mechanical fasteners, such as welds, bolts, and rivets, to advanced structural adhesive and sealants. This transition is driven by 3 key requirements. First is the weight reduction. It is to improve fuel efficiency and extend EV range. Second, enhance vibration damping to deliver a quieter and more comfortable ride. Third is superior stress distribution. Adhesive spread lots across the entire bonded area, unlike bolts or welds that concentrate stress at specific points. However, this advancement introduces hidden vulnerabilities. Under extreme conditions such as high temperature, high humidity, or manufacturing inconsistencies, this adhesive can degrade or become highly resistive electrical insulators. This creates a serious, often overlooked risk: vehicle fires.
We will continue on actual issues occurred by the OEMs. Now we will review the actual adhesive failures experienced by major automotive manufacturer. Example, in 2010, Ferrari had to call more than 1,000 of its 458 Italian models. The root cause was the adhesive used in the exhaust issue was softened and degraded, eventually catching fire under extreme engine temperature. Another major issue is resistive heating caused by the manufacturing defects. Both General Motors, GM, and Ford recall over hundreds of thousands of their trucks, respectively. During manufacturing, the adhesive squeezed out, coated the external alternator and the battery cable outlets. Instead of conducting electricity, this excess glue acted as an electrical insulator, which led to high resistance, melting component, and eventually fires in the engine component. Moving on to the next issues, we see that adhesive failure are also triggered by environmental factors and rapid shift to the electric vehicle. Honda faced the massive recalls of over than 1 million Accords model because of the sealant on the battery sensors broke down due to the moisture and hydrolysis. These failures allowed conductive salt water into the sensor, causing short circuit and more smoke. As the industry transitions to the electric vehicles, these problems have evolved. Porsche and Audi had to recall over 40,000 electric vehicles because poorly sealed adhesive seemed let the moisture directly into the high voltage battery packs, leading to thermal runaway. Just recently, Chrysler recalled over 300,000 plug-in hybrid for alternator wire adhesive failures, and Ford recalled over 200,000 EV due to a loss of internal cells adhesion within the battery pack itself. This clearly shows that adhesive reliability remains a critical safety challenge across brand new vehicle architecture.
Okay, let's look at the impact of adhesive failure on manufacturing, product quality, and operations. First, manufacturing. The core issue is squeezed out excess adhesives on battery terminals, as seen with GM and Ford in 2019. That glue acts as an insulator, causing heating, arcing, and fires. OEMs now use UV tracer additive and optical inspection to catch this, but there is still no standard to measure conductivity from adhesive joints. Second, product quality. These are serious safety defects. Honda's recall of 1.15 million could destroy consumer confidence and lead to a 10-year warranty. Ferrari's supercar fire damaged its brand. Even if less than 1% of recall vehicle catch fire, one incident can cause death and massive liability. GM paid over $120 million in settlement. Third, operational efficiency. Recalls create logistical chaos, locating millions of vehicles, sourcing new parts, inspecting thousands of dealers. In 2024, Chrysler taught dealers to park 338,000 jets outside due to fire risk. In 2025, Ford used a smart recall, a software update limiting battery charge to 18% until physical repairs are done. Finally, legal repercussions. The NHTSA has fined companies and issued consent orders for delayed reporting. The bottom line, adhesive failure is no longer a small technical problem. It is an operational and legal issue on the board agenda. Next, we will discuss the strategy OEMs have implemented to solve this problem.
Okay, welcome to the section on strategies and solutions, where we will first examine the physical inspection and rework. Manufacturers like General Motors and Ford primarily utilized physical inspection and rework to address resistive heating issues in 2019. Dealership technicians were instructed to manually inspect suspect adhesive zones, technicians were directed to carefully remove excessive sealant or adhesive from the battery cable eyelet and alternator terminal. In instances where manual inspection revealed severe damage, such as melting or arching marks, the entire affected cable assembly or wiring harness was completely replaced. Okay, for direct component replacement, alternatively, direct component replacement was the primary solution used by automakers such as Honda and Ferrari to address failures related to moisture ingress and thermal degradation. Honda instructed its dealerships to replace faulty battery sensors with newly engineered units that featured enhanced sealing capabilities. Similarly, Ferrari mitigated thermal degradation by replacing existing underbody heat shields and their associated adhesive components. Ferrari's replacement materials were specifically designed to withstand significantly higher operating temperatures. Okay, continuing with our strategies and solutions, let's look at how the industry handles hybrid software level mitigation. To address recent electric vehicle battery adhesion failures, original equipment manufacturers, including Chrysler and Ford, transitioned to a hybrid software level mitigation strategy in 2025. The first phase of this approach involved deploying a software update design to cap the maximum battery state of charge. For instance, Ford proactively limited battery capacity to 80% to minimize the immediate risk of thermal runaway. Once the software limitation is safe in place, the secondary phase requires scheduling a physical dealership appointment. During this appointment, technicians thoroughly inspect and, if necessary, replace the compromised battery modules. And for industry-wide strategic shifts, moving to broader industry-wide strategic shifts and quality control, these component failures highlighted an industry lesson regarding the necessity of design and process redundancy. This realization has ultimately led to mandates for hybrid assembly methods. Manufacturers now emphasize redundancy in high heat zones by combining physical fail-safes like clips and rivets alongside traditional structural adhesives. This hybrid assembly method is particularly prioritized in areas adjacent to high voltage terminals and exhaust systems. To ensure rigorous manufacturing standards, some manufacturers now requires the integration of ultraviolet fluorescent traces into all electrical and structural adhesives. The use of these traces facilitates rapid and non-destructive optical quality control directly on the assembly line.
So the lessons learned and the implications in the automotive industry. First, static quality checks fail against latent defects. Standard factory lines often miss micromillimeter adhesive overflow. These tiny imperfections look fine initially, but they can lead to catastrophic failures down the road. So to prevent this, we must adopt proactive protocols. It is a highly effective solution, which is standardizing fluorescent traces within the adhesive formula. They remain invisible under normal factory lighting, but glow vividly under UV black lights, which is allowing inspectors to catch minute defects before assembly is complete. Our second lesson focuses on environmental conditions. Mechanical redundancy is mandatory in high heat zones. While modern structural adhesives are incredibly strong, they cannot act alone near high thermal environments like exhaust systems, where sustained heat degrades chemical bonds over time. Therefore, high temperature applications require a hybrid assembly approach. By combining adhesive with robust mechanical fail-safe like rivets, we ensure that even if the adhesive experiences thermal degradation, the mechanical joint prevents a total structural failure. Next, micro-contamination triggers micro-financial risk. A mere 10-cent application of excess glue on electrical terminals can create a soft joint. This prevents proper fastening torque, which will cause connections to loosen over time, arc, and ultimately ignite. Then, environmental stress accelerates interfacial debonding. In coastal and saltbed regions, moisture and aggressively degrade adhesive seals within 5 years. So to counter this, component sealants must undergo rigorous pre-production vibrational and electrolytic testing. Finally, software diagnostic must offset hardware delays. High voltage EV adhesive failures can lead them to rapid thermal runaway. Because physical fixes take time, the industry must leverage smart recalls. By using real-time telematics and interim 80% charging caps, we can detect early degradation signatures and mitigate risks before a fire occurs.
Thank you for your time and attention. Be happy to take any question and discussion further. Before we end, we would like to express our sincere gratitude to our lecturers. PS Dr. Izuan Amin bin Ishak, and Prof. Mutalib for your guidance, support, and valuable insight throughout this project. Your knowledge has greatly helped us to complete this presentation.